Hello, hello. Can you guys hear me? Good, brilliant. Good evening, everyone. My name is Jules Damji. I'm the developer advocate at Databricks. Delighted to actually all of you here today. I know there's a lot of traffic to come here, but we are really happy to host our first Bay Area MLflow meetup here in the South Bay. And I really want to call out a few people who have really given us a lot of support to host this. Subru and Avrilia and Carlo, give them a big hand for Microsoft. All the food and all the events has been organized obviously by Kyle, who's been sitting outside helping. And I've been told that the food is going to be there till 7:45. So if you want to have seconds, make sure you actually have it before. So before we get started, a couple of announcements. We have a Spark AI Summit coming up in October in Amsterdam. So if Amsterdam is on your bucket list, please feel free to come over. It's actually a great place to meet a lot of people, a lot of data scientists, a lot of things actually happening in the open source. And our first speaker today is Subru Krishnan. He's one of the principal data scientists here doing research in the ML platform. And he's going to talk about Flock, what they're actually doing to make the data science life easier. So please give a warm welcome to Subru.
Thanks, Jules. Can everybody hear me? Okay. Thanks, Jules. So we're going to talk about Flock, which is a data science platform we're building here. So the agenda is going to look, so we have two chapters. So the agenda is going to look like, I'm going to say first give a brief intro about who we are. I promise you this is not mandatory spiel. This is some context for what we are doing as well. And then we're going to talk about why are we building one more data science platform, right? We need to have some justification for it, right? And then we'll talk about the idea of the Flock platform, and we'll demonstrate what the capabilities of the Flock platform today is. It's very much under development, so we'll demonstrate it with a technology showcase demo, right? And then Avrilia will take over from there. She's going to talk about ONNX. How many of you here have heard about ONNX? Okay, it's good. So we have good coverage. She's going to talk about ONNX, and then she's going to talk about something interesting happening in MLflow 1.0. After all, it's an MLflow meetup. So she's going to be talking about MLflow and ONNX, and some of the future exciting work we're looking at here, right? So who are we? So we are part of Azure Data Office of the CTO. We're a research lab. So we have two teams. So one is CISL. So it's a Cloud and Information Services lab. So CISL is based out of Bay Area and Redmond. So we are here in Bay Area. So you're talking to folks in CISL here. And then we have a GSL, which is a Gray Systems lab, which is based out of Madison, right? GSL has been traditionally, they've been working very closely with the SQL products in Microsoft. And as CISL's name suggests, we've been looking at a lot of the big data cloud stuff happening here, right? So we wear three hats in the organization because we're an applied research team. We're not MSR. We're part of the Azure Data. So what do we do is, so our research is tied to product, right? So what our VP calls us is we are the team which looks around the bend, kind of, right? So that's mainly our charter. So look at the next of the product, kind of, right? And we collaborate with Azure Data Product Group. Collaborate is putting it mildly, they pay our salaries. So we better work with them, kind of, right? And we have fun doing so. And then we have a third hat, which is like we open source, work with the open source community, right? That's why we are here hosting the MLflow meetup. So we've been very actively working with the Hadoop team for like 6-7 years. We've been working with the Apache Heron team, etc. And then pretty recently with MLflow. So this is the talk, right? Let's walk the talk, right? What have we done actually, right? It's all good and well and good to say we wear three hats. What exactly have we done, right? So we've been around from early 2012. So what we have done is we have about more than 1 million lines of code in Azure products, which is live. We have about 500,000 lines of code which have contributed to the open source projects we talked about. We have our software running in more than 600,000 servers in Azure. Because we are an applied research group, we do a lot of publications. You'll be hearing about that as the talk goes along. So we have publications in about more than 130 publications in top tier conferences. We have 37 patents, and again, going back to the collaboration, working closely with the product. We have 6 at least features which have contributed to Azure just this year, kind of, right, in the past year. So this is what we are. And so what we have been traditionally, why this is important is, we have been traditionally being systems building group, right? So we've been building large infrastructures. So some of the project is to, like the last project which Carlo and myself, we were involved with Costas and folks here, is to scale Hadoop to 50,000 nodes. So we have the largest Hadoop clusters in the world. So they are north of 50,000, and we have more than 300,000 machines running Hadoop now, internally, which is powering Bing, Office, Windows, etc., right? So we have traditionally been a hardcore systems building team, right? But as we build, we have been building systems for a while. Data sciences has been creeping in slow and steady, right? So a lot of the solutions we recently do have an element of data sciences, ML involved. So what we realized when we started seeing this trend, we've been seeing this trend not just with our group, right? We see it in Microsoft and outside. So as part of our charter for saying, looking around the bend, right? So we see this trend, and then we decided, okay, let's get a more formal feel of what's happening, because this is a gut intuition we're kind of feeling. And for the demo, I'm going to showcase one of our actual production system, which actually is a data science solution which we are running in production for one of our clusters, right? So I'll also give an idea of grounding all of these ideas, right? So what we did is we looked around. So we have 3 buckets where we looked around, right? So we looked at the cloud providers. So the big ones, let's say, the Google, Amazon, and the Microsoft. We looked at private, what's happening in private. So this is more a sampling, right? So we talked to LinkedIn and Uber because we've been traditionally working with them. And they had a lot of interesting blog posts and papers around it. So we thought it's a good folks to talk to. And we also looked at a couple of projects which seem to be getting a lot of traction in the last 12 to 18 months, especially in the open source. So particularly Kubeflow and MLflow, right? So from this, we have a survey. So a couple of disclaimers, right? This is by no means exhaustive, right? You guys are all here. And the level of innovation at the Valley is very hard to keep track of. But this, we feel, is a reasonable sampling of what we have done. And what we've also tried to do is be unbiased, right? That's part of why we have kind of put our context, right? So we do open source, we do publications, so we try to stay as unbiased as possible. And this is what we kind of like. So what is it that we observed, right? So there is a lot of work happening recently to kind of get data sciences and ML development into the SDLC kind of world, right? So people call it software, some people call it software 2.0. So how do we get it to the level of maturity of what traditional SDLC has been, right? So a lot of the work has been on, obviously you have the training, a lot of the work has been on training. So we have, so this slide is going to be pretty dense. So I'm going to just point out a few highlights. And then the slides, I think we'll have the video and slides available, so you can take a more look at it kind of offline. And another thing is, this is a snapshot. We did this about 4-5 months back. I'm sure the community, a lot of these people have been making a lot of progress. So you'll see some things which have also changed a little bit there, right? So, and part of some of the challenges we had is, for example, when we're looking at it, we went to the Amazon and Google websites. We couldn't find 2 very clear documentation about what they're doing for experiment tracking, right? We're very reasonably sure that they have some stuff happening there, but it's just that it's not very clearly called out, right? So, and another thing is, there is AutoML. So there is part of this, which is the last line is important, because that's something which can really help kind of reduce the barrier for data sciences. But that's not, like, if you see, it's universally kind of great, right? So the AutoML work, everybody calls out AutoML, they'll show you some good examples, and then you go talk to a real production system, there is a lot of problems, right? We'll also talk about why one of the huge gaps, one of the big reasons for having these gaps, right? Which will be like and then we have the other aspect, which is serving and deployment, right? So here also you'll see a few trends I'll just call out. Is like, there is generally good support for having serving and on-prem serving, but not so much for model monitoring and model validation, right? this is again a sign of the maturity, right? So if you think about it, you deploy models, you want to keep monitoring. So if you have traditional software, you're monitoring what the software is doing. You have the metrics, all this collecting. You have rollbacks and all of those mechanisms built in. You're also validating what the results of the calls are, and you have APIs which are syntactically very strong way to validate those. With models, the syntax is not maybe the right way to look at it. It's more semantic. So that brings in the challenges. So if you see model monitoring and validation is an area where there is quite a way for all of us to go. And then the biggest problem, right, and is data management, right? So that's one of the reasons why we also have the gaps with AutoML and all of that, right? And if we observe what we observed is, if you looked at the proprietary systems, which is LinkedIn and Uber, which have systems which are not open source, which LinkedIn is called ProML and Uber is called Michelangelo. They have very good blogs. So if you guys want to check them out, but you won't see the code, obviously, it's proprietary, but they have very good blogs if you guys want to check them out. So if you look at it, they do a great job of data management, right? But they do a data type. It's also one of the reasons why they are in production. It's also, the flip side is they're also proprietary, because you have data sources and data formats and all of that, which is very private, and you have a lot of non-technical, legal and GDPR kind of reasons while this is happening, right? While it's a struggle for people who are sitting outside that, who are outside the company, who are outside the company walled garden, if you want to look at it, to deal with this explosion of data, right? So so what are the insights we gained from doing this survey, right? So we, obviously, the first thing is, it's all about data, right? It's all about data. That means quality of data, labeling, for example. People don't traditionally do labeling. And if you look at a lot of the academic works, they do assume labeling. Some don't, but they're not maybe very easily applicable. Then you have the quality, like quality of the data as well. So that's another thing. And you have access to data itself. So data is in different formats and different sources. So just in Microsoft, in the Azure group, we have we have the blob stores, we have SQLs, we have NoSQL. So everywhere, the data is spread over everywhere with different formats. How do you get them together, pull them together, kind of, right? That's always the biggest challenge, right? And then, okay, so this is like, all of this are maybe obvious in hindsight, but it was not, like, think of it as almost like getting there was pretty hard. What we realized is data scientists are not programmers, right? So they are good at doing the math and all of that, but if you tell them to do, okay, write a program around that, you will not see something which is kind of useful, right? So data scientists are not programmers, and then this is what you see like a tangential pressure, right? And this is something which takes time to wrap your head around, because you talk to data scientists, they'll have this freaky math stuff showing you. So you think, oh, this is pretty advanced. So it's pretty advanced science with pretty primitive processes, okay? So this is something we need to kind of help out. And then this is what, as programmers, we have the gap with data scientists. And the data scientists also have some gap with the programmers, right? So what they say is, okay, you say, okay, we need something. They'll say, okay, we have a model. So we want to do forecasting. They say, we have a model that does it. Okay, take it, use it. That's never the case in real production systems, right? An output of an ML model is rarely directly usable. You get a float numbers. You get a vector of floats. Okay, what do you do with that, right? So what you need is something which is, we need to make a very context-aware, system-specific action from the models, right? And this is something which is very much in the programmer's domain, right? So with all of this, we thought that, okay, there is a play for us to do a data science platform after all, even though it's all of us working on it, right? So what we want to do is pretty simple. This is the epiphany we had, right? All we want to do with our platform is let data scientists do data sciences, right? You talk to any data scientist with any project, they'll tell you that they actually end up doing about single-digit percentage of their work actual data science, right? How many data scientists are here in the audience? It's all a lot of, okay, we have very few, we have a lot of programmers, kind of, right? So we did talk to quite a few data scientists, and this is what they actually spend about single-digit percentage of their time today in actually doing data sciences, right? So the corollary of this is we also let programmers do the programming, right? So that's the unsaid corollary of this, right? So how do we think about going about doing this, right? So that's where we have this flock, what we're thinking about. We call it a data-driven development. Okay, so we have your data. Obviously, like I've talked enough about it. So we have data. So from the data, you're going to do the cleaning, validation, featureization, which that's a standard process, and then you have your model training, right? So the output of that is yep. Yeah, please, free. Yeah.
What makes you believe that a programmer who are engineers will
Yeah.
not be data scientists?
It doesn't preclude them from being data scientists at all, but they are better at doing programming. Is all. Yeah.
Right.
Yeah.
That's the role. I mean, every technical design from the assembly statistics. So why would they not go up to data science?
So there is a specialization with the data sciences itself, right? So we have a few PhDs who are data scientists who have just spent 6-7 years learning how to model it, just learning the math and the science behind it, right? Yeah.
If someone is a Ph.D. from, let's say, chemical engineering,
Yeah.
and if they can become data scientists, then why can't they computer science graduate become a data scientist?
They,
I think the high-level argument with this platform is to say, we don't want you to first do the data science and then have to rewrite all of it in Java, C#, C++. Is do your data science in Python and all of the mathematical formulations you love, and then ideally you click a button and magically this becomes a scale-out, productizable object. That's the direction.
no, it doesn't. Like nothing precludes anybody from doing anything. If it's a very generic question, right? But it's a lot of time and effort. It's a specialized field, right? So, okay, and so we have the model training, and then we do the model transformation. Okay, part of the reasons for doing the model transformation is there is an explosion of the surface area where you want to get the model out, right? So before you used to have the servers on-premise of your company. Now you have the cloud. Now forget that. Now you have your phones, your tablets. You want to have some models running there. You have some IoT sensor devices which is running really in the wild. So we want to get to transforming the models so that it is universally available, right? So that's part of our transformation process. So what we do here is, Avrilia will talk about ONNX, but since most of you heard of ONNX, I'll just call out that what we do is kind of transformation of the traditional ML models to ONNX. And here you can see that we have a hyperlink, like this is one of the promise. So we have a paper publication for this. So the link is there, so you guys can follow it up. So what it does is we take a traditional ML model, convert it into a neural network, so that you have an ONNX model available, right? And then we also do some optimizations on ONNX, right? This is also a few of the optimizations we are doing. Avrilia will talk about it, and we have folks like Costas who are around after the talk to also talk more about what is the things, like what are the cool optimizations working in the ONNX runtime. And these optimizations are also targeted at specific. So a lot of the ONNX optimization is also done by the hardware vendors. For example, Intel and NVIDIA are working hard also to optimize ONNX to run better in their hardware, right? So we get those, right? So let's say we have an ONNX model now, and then we have an optimized, we call it ONNX Prime. And then when all of this happens, we want to do tracking, right? That's part of the standard, like we said, get the SDLC to ML, right? So that's where MLflow comes in, right? So again, one of the reasons for talking about who we are is we do a lot of open source, so right? One of the mantras we follow is proudly found elsewhere, right? So we don't want to rebuild stuff which exists, which a strong community is working on, right? So we kind of build on those, right? So we take MLflow, we contribute to it and use it. And there is also an Azure ML service, which we have been working very closely with the team. So that's also aligned with MLflow. So you have the same APIs working over Azure ML or MLflow, right? And then you deploy the MLflow model, right? And then we talked about, we have some set of policies. So think of them as like state machines, right? So the demo will give you more clarity about that. So the system is called Dalian. Again, there's hyperlinks. This is also available. The paper is available. There's also the open source. So again, going back to who we are. It's open source system. We already use it in production for the HD Insight Azure service. Twitter uses it for SLOs for their streaming graphs. Netflix is using it. But this is something which came from traditional systems, which allows you to write policies. So we have a wrapper of the policies around the models so that the results from the model can actually be translated to some actions. And in the demo, what we're going to do, for example, is we have a system. I'm going to talk about it. So in the next slide, actually. So we have a system which is I'll talk more about it when the slide comes. So effectively what you get is we have a lot of jobs running in our cluster, and we want to debug what happens to a job, right? So we get a job ID, and we look at the model, and we give you some, so we'll talk more about it, right? So in essence, what we want to do with Flock is, like we said, we want to let the data scientists do data science, right, and just remain there. So we want them to concentrate on just doing the model training and coming up with the model. And we want to do all of the rest of the systems stuff we talked about, right? If you have such a complex flow, we are not really making anybody's life easier, right? If this is the flow which has to be followed. So we want to do it automatically, right? So in essence, all we want to do for the user is just write a small piece of code, which is the user code. And then we have the instrumented code, which we generate, which has all of this, right? So with this, I'll do a demo to demonstrate this, right? And for the demo, like I promised, we're going to use a production system which we use. It's called Griffin. Here also we have a paper, which it's very new, so it's under review. So it's under submission, we have it under review. So what does Griffin system do, right? It answers this question, why is my job slow today, right? So we talked about clusters, right? We have clusters which are single clusters which are more than 50,000 nodes. And we have more than 300,000 machines which are running Hadoop, right? So what we've done is a lot of work from our previous systems background is to bring up the reliability, right? That's been the work which has been happening for decades effectively, right? So we have got the reliability to a few nines, but so we thought, okay, we've made everybody's life easier. So the cluster is rock solid now. You run your jobs, you're fine. So we started getting into more trickier questions like predictability, right? So now that the jobs don't fail, people are like, yesterday I remember my job ran much faster. Why is it running slower today, right? That's a much harder question to answer than just a job failure, right? So we moved to that now. We moved the needle to that kind of, right? So how does that happen today, right? Once this question is raised, right? We raise a ticket, right? So today, what's the flow, right? Before Griffin was deployed, right? A job goes out of SLA, and then a support ticket is raised, right? My job is slow. What happened, right? And then somebody has to go look at it, right? Debug the job. So we're collecting all the metrics. We're very great, right? We collect all the metrics, which is what's happening to the job. But the catch is some of the jobs, or most of the jobs, are running on thousands of machines, right? So to go isolate a cause for a slowdown is going to be, because the distance, the gap between the cause and effect is pretty large in this large-scale distributed systems, right? So you have few people who are experts at debugging, who will go look at it, and even with them, they'll take a few hours to say, okay, this is the reason why this job was slow, right? And what do we want to do now there, right? So we say, okay, part of what happens is about the predictability. Is if your job is slower than yesterday, that means your job ran yesterday, right? So what we have is 70%, 2/3 of our workflow or more is recurring jobs, right? They're the pipelines which make money. They're ad pipelines, et cetera, right? Click log, whatever, right? So they run every hour, day, week, whatever, right? They keep running on a schedule. So we have the history. So we look at the history of the job runs and kind of have a model for how an execution of this job should be, right? And then when somebody says this job run is not great, it's slow, we go compare with our modeled version of the job execution and say, okay, in this run, this is the factor which has changed, and that's why it could affect your run, right? For one of those examples is your input changed, right? So you had, like, you're doing delta changes, and then you had a full kind of data, right? So we could identify and say input is what has changed, and it's usually about a terabyte. Today you have 50 terabytes, right? So we give you a weighted list of factors which affected this particular run of the job. And we do something, we actually do a categorization, right? We categorize the tickets when the users raise a ticket to user or system, right? What does it mean is, like, as example of user is data, capacity. So you are running your jobs with 1,000 VMs. Today you decide to run it with 800 because you maybe had another job, right? That's something which you decided to do, but that will cause a job slowdown, right? We'll identify that and say, mark it as user, right? What is system, right? We could have some slow nodes. We could have disk failures. When you have tens of thousands of nodes, you have some disk failures, you have a top of rack switches failures and all of that, which is a system thing, right? So we identify that and say, okay, this is what caused it, right? So this is what Griffin is about, right? So and what we're going to do in the demo is, because it's obviously a demo, and like I said, this platform is very much work in progress, we're going to take a distilled version of Griffin and show it. So I'm just going to switch to the demo. Any questions meanwhile? Okay. Can you guys see it? Is the font visible for folks? Okay. So if you look at it, what we have here is what ideally we want the data scientist to do, right? It's a simple binary classifier. We just use a LGBM classifier to classify. So right now we're taking the first part of the problem to classify whether it's a system or user, right? So all it does is it takes the training data, does a fit and classifies whether it's a user or system, right? So it's pretty simple. It's, I don't know, it's about 15, 20 lines of code if you like disregard the white spaces kind of, right? So the mouse is, okay. Yeah. And now we have our Flock system. And what we want to do is, like we talked about in the slides, we just pass in the script and say, okay, let's do the ONNX optimization on the script, right? So what you see below, and the color in blue is what the code we generated, and if you can see the normal black is the exact demo code, right? So we just want to highlight what we generated. So what we did is we take the simple binary classifier, and then we generate a PyTorch kind of, we generate a DNN model, right? So this is something we can do. And then let's say we want to do MLflow tracking, right? All of us are here to know about MLflow, and MLflow is very useful. So we want to do MLflow tracking for this model, right? So now we can just run an MLflow tracking, and as you can see in green, we are adding the MLflow imports and the tracking. Okay, the question becomes, why do we need to do this, and why not let the data scientists do it, right? There are at least a couple of reasons, right? One is when we have a lot of existing code, right? Some of the code which we have in Microsoft, even which are done by interns or some employees or not even around, which runs in production kind of, right? So you don't want to leave those things out of the picture. So you want to get them into the thing. The other thing is you want some consistency, right? So you, for example, Avrilia, me, we work closely, but we might still do things differently, right? We might slightly do the logging or tracking differently. But if you let the system generate it, you have a consistent format, right? So you have some consistency here, right? And now, let's say we want to do all the things we talked about. So we want to do the MLflow tracking. We want to do the ONNX optimization, and then Avrilia will talk about the new feature in MLflow 1.0, use MLflow to save the ONNX model and deploy it, right? So that's the pink line. So we can do all of that. And now that we have generated the code, let's take a quick look whether this actually works, right? All of this is fine and dandy to talk about. So we just take the code and run it, and you can see that we have a score, and we can go to MLflow and see the tracking, right? So we have it. So yeah, so if we can change it, yeah. So yeah, we're out of time. So that's about the demo, right? Okay, so Avrilia, I'll just sign off. Yeah, we have to shift to the. So we'll be around. So if you have a few questions or anything about this, we can talk about it. Yeah.
Are you doing this to every program that's in production, or just the ones that are having problems?
So we want to do this for every program in production. We want to do it. Okay. So right now we're starting with actually we're starting with the newer projects, and we want to get to the North Star is to get to all the code.
What's the impact on the overall performance?
So a lot of this is at training time, right? So Avrilia will talk about how the inference we make it actually go faster. So all of this is in training time. So we're fine, kind of, right? We want to do this. Yeah.
Yeah, so how much time do I have? Okay, it's fine. Yeah, so I'll talk a little bit about ONNX and the work we've done to integrate ONNX with MLflow. As Subru mentioned, ONNX is a central component of our Float platform. So the basic idea is the following. We have a bunch of frameworks to do training. There are so many options. But then eventually when we have a model, we might need to map it to different devices for inference. We might have CPUs, GPUs, cloud, mobile devices, and so on. So if you see, there's like end-to-end connections here. So what ONNX is trying to do is to create a standard format that will facilitate this process moving from the training to the inference and sort of have optimizations for different hardware. ONNX is an open format to represent machine learning models, DNNs. It's backed by Microsoft, Facebook, Amazon. And as you see on the top right side of the slide, there are multiple companies that are actually collaborating on this project. So it's getting a lot of traction. Okay, so yeah, ONNX is open source. It enables interoperability across frameworks, so you can basically run your training in TensorFlow, generate a TensorFlow model, convert it to ONNX, and deploy into inference using ONNX Runtime. And we have connectors to many different engines like PyTorch, TensorFlow, as I said, scikit-learn, and so on. So as you see on the right side, ONNX essentially it's like a database internal representation. It consists of a set of operators. Instead of database operators, we have machine learning operators. And yes. And to do actual inference on ONNX, in Microsoft, we have developed the ONNX Runtime, which is a cross-platform high-performance inference engine. So it works on Windows, Mac, Linux, and it has support for different hardware, CPUs, GPUs. As Subru mentioned, we have specialized backends for NVIDIA and Intel hardware. ONNX Runtime was open source at the end of 2018. And it's currently used by millions of devices internally and actually different orgs like Office, Bing, and Azure. So the idea is the following. We train a model using a popular framework, TensorFlow, scikit-learn. Also, it could not be open source internally. We have different engines as well. We convert the model to ONNX, and then we deploy and run inference using the ONNX Runtime. So ONNX Runtime essentially operates on a graph internal representation. As I said, we have support for multiple backends. And because the internal representation is a graph, we can do multiple optimizations on the graph to improve the inference time. So ONNX Runtime currently has a rule-based optimizer similar to what databases initially have. So basically, the optimizer goes through this internal representation, does some pattern matching, and applies a set of rules. So one rule, for example, could be these three operators could be fused. And then you can do that recursively and sort of optimize the graph in a recursive way. So Kostas, who is also here, worked on a bunch of these optimizations for ONNX Runtime, and the goal is basically to improve inference time and memory consumption. So an example for one of our models in production, with the optimizations we are doing on the graph, we can reduce the inference time from 120 milliseconds to 34, and the memory consumption by 50 megabytes. And this is still work in progress, so we still keep improving. So in production, we currently have about 40 models in production, but there are a lot more that are actually in the process of migration. And this is going across 10 different orgs in Microsoft. As I said before, ONNX Runtime is used by Office, Bing, and other Azure teams. And we have an average speed up in inference time of about 2.7x. Compared to other frameworks that have been used before. So that's a good speed up. This is an example you can also find online in some of our blogs. After we deployed the model after we started doing inference using ONNX Runtime on one of the models used by Office team, there was an improvement at about 14x in latency, and you can see like the graph how it changed when the ONNX Runtime was deployed. So now we want to track these ONNX models. We want to do better model management on ONNX models. So in our lab, we decided to integrate ONNX with MLflow. So now MLflow release 1.0 has built-in support for ONNX. We collaborate with the Databricks team to have this contribution. So essentially what we introduce is an ONNX model flavor for saving, loading, and evaluating ONNX models in MLflow. So this is an example, a script similar to the one that Subru showed before. Basically, we train a scikit-learn model. We collect some data, we train the model, and then we have two lines at the end of the script. The first line essentially converts a scikit-learn model to an ONNX model, and this can be done through the standard packages, ONNX ML tools or other converters provided by the ONNX community. And then we can actually say, invoke the appropriate MLflow API to log this model. So when we log this model, we can see locally that it basically follows the MLflow model format. There is an ML model file that describes that this is essentially an ONNX model, what is the version of the model, and what flavors are supported. So apart from the ONNX flavor, we also support the Python function flavor, which basically means we can wrap the model in a Python function and perform inference on that model. And an example of that on how we do serving, we can basically deploy the MLflow server with the usual MLflow serve command. And then we can pass some data. So this command essentially sends a JSON serialized data to the server, and we get an output, which is basically the float number shown in black. So what this does is underneath it invokes the ONNX runtime to actually do the prediction. And all this is done through the Python function flavor that we implemented. So now I'm going to talk a little bit about the future work, what we're planning to do next in MLflow and in general in Flock. So in MLflow, we want to work with better integration with relational databases, in particular with artifact store. So we see in Microsoft in many applications that people have their data in SQL Server, and they want to not move the data outside SQL Server, so they want to do their machine learning and inference through SQL Server. So we want to enhance MLflow to support storing models in relational databases and find what are the appropriate abstractions to do that and how to extend the existing code. We also want to integrate MLflow with metadata management systems such as Apache Atlas. This is something we are considering in the context of provenance. We want to basically track how users transform the data and generate models through Python scripts and through MLflow, and capture all these informations and use them for debugging or providing more insights to the user. Then in the context of Flock, as I said, provenance, data governance are two areas that we are actively looking into. We want to see how the data is connected to the machine learning models, what transformations the users are making, and essentially create good abstractions to represent these relationships so that people can actually query and get insights from these relationships. And as Subru showed in the demo before, we have done some work of doing automatic tracking of in our Python scripts, and also converting traditional ML models to neural networks. So we want to generalize and extend this work to make it cover more Python programs. And with that, I think I'll take any questions.
Thank you. Yeah. That was fast.
Yeah.
I didn't mean to put you under pressure. We have another mic. Do you have any questions?
Yeah.
What hardware platforms have you run MLflow, your runtime on? Can you just enumerate them?
What?
What
Hardware?
platforms, like what type of clusters?
For MLflow or for MLflow, we run first of all in Azure VMs. That they had. What is the hardware behind?
So Azure VMs have a lot of SKUs.
Yeah.
SKUs. We've run it on-prem. Azure VM. So we also worked with a few folks, Sid and folks in the MLflow community to have it working on Windows. So we have run it on Linux as well as Windows. MLflow, I don't understand the question to it because MLflow is part of training, right? So
Yeah.
we're not worried about the performance or it's part of training.
Of model management, basically.
I think he's asking if you've been running on FPSU because I know.
That's the ONNX Runtime.
Yeah, the ONNX Runtime. He's asking about ONNX Runtime.
So MLflow is for training, so we run it normally on VMs, right? And for ONNX, we, like Avrilia mentioned, right now.
So it's running in multiple devices, mobile devices, cloud, CPU, GPUs, and different parts of the org are using different infrastructure. So depends on the application.
Any other question? Okay, sure. We got time. All right, give a big, oh, yeah, you go.
Tracking separate because some ML systems they'll retrain the model based on more information, more transactions coming through every day has to be retrained. Does the tracking work separately for those changes versus a data scientist changing the algorithms and how it's composed?
So that points to the provenance work we want to do right now, right? So today the answer is no, right? And that's one of the reasons we feel there's a rich scope for work is to have provenance, right? So track where the changes are from and get to a point where you can track decisions from the models all the way back to the code, right? So that's why that's part of the future work. Provenance is something which is very exciting for us.
Any other question? We'll take the last one before we switch.
Thank you. Can we use MLflow for classification in the classification of images? I'm sending the data as an image and classifying dogs or cats.
So you can, and I think Matej, who's going to talk, Clemens and Matej are going to talk next.
Yeah, we'll answer that question.
Even better people to answer that question than us.
We'll have that.
So we'll let Clemens and Matej answer that question for you.
Any last one before we switch? Let's give a big hand to Avrilia and Subru, and thanks a lot for hosting us. Did you guys want to take a couple of minutes bio break? There's a bathroom across. If not, we're just going to go straight into it. Okay. It'll take a couple of minutes to set up, so if you want to take a bio break, and the food is going to be done in about another half an hour, so if you want to have seconds.
How do we switch this to laptop?
If you're wondering where the toilet is, just go out the door, make a right, and then a right again. And see you here in about 5 minutes or so.
You should use this handheld.
Yeah.
Yeah, because if you're going to be...
That's good, then I'll use this one.
You guys hook it up.
So now you should be able to, you're all set to go.
You want...
Yep, got it.
Is it hooked up?
I'll have a short thing, then I'll hand this to Richard.
Okay, so you're going first?
Yeah, I guess I'll start, and then I'll introduce Clemens. And then you introduce Richard.
And then Richard has his own laptop, right?
He has his own laptop, so
We'll switch it.
should be okay.
So we'll just give them about a few minutes.
Yeah, just wait till whatever we said.
I'm gonna actually ask how many people give them. There's like a lot of discussion. There's a lot of transportation. It's very obvious that they don't know.
Yeah, they just don't know it. Maybe it's good to spend some time.
So that's how I'm on
MLflow, yeah,
how much
so
I
next
on the slides.
Yeah, that's a good idea.
If like everyone knows MLflow, then it's fine.
Yeah, that's a very good
But if everyone thinks it's like
Yeah, what is it?
everyone thinks it's in like TensorFlow.
Yeah, I know. It's a problem.
Yeah. But you get this at
Yeah. Okay, makes sense. So yeah, my part will be pretty quick.
yeah. So you'll have to switch actually, and I don't think this will work. Yes, you'll have to switch on the laptop.
Yeah, that's okay.
Are you using him? Oh, you.
No.
So we gave a time
talk and spark some.
Enjoying the talk, yeah.
I was a bit fast, I got scared.
Oh, yeah, it's okay. It worked out.
Okay.
Yeah.
No, so I mean, you packed everything in ONNX. It was actually good.
Yeah.
Yeah, it was great, yeah.
I think that's a big contribution.
One thing I was curious is how does ONNX Runtime do compared to TensorRT?
I haven't really done personally a comparison. I've seen some data. But again, it's not that I generated. I've seen data with speedups from 1x to 15x.
I see, over Tensor.
I don't know if it was only TensorRT was part of the list, but I don't know how much. But I can look into it more and see what we can sell. Yeah, because personally,
I mean, TensorRT is only for GPUs also.
yeah.
But it's another thing I've seen in the US.
Yeah. I'll come back. Yeah, sorry.
Yeah, I can write it down. Yeah, so what I'll do is I think I'm going to talk to my engineering guys. I believe what they were saying is we can compile something like this. We can compile our original Are you located here?
Yeah, here. And the only
Yeah, I'm almost sure that that's the Azure basis. So our company is just a little bit of a startup in Portugal County. But a lot of success. Starting in TensorFlow. So they're using representation. I don't think they're using real runtime per se. Like your runtime is just reducing that data. And optimization. So we would be complementary. So we take the output of the company.
Good. Yeah. I'm sorry I had to tell you because we didn't want to do it.
Yeah,
45 minutes was
but we had time. I thought I had to cut short the demo. I had a little more of the demo. I thought we were running out of time, and then Avrilia finished earlier.
Yeah. Well, I mean, 45 minutes normally are good, 45 to 50, and plus there are going to be a lot of questions as well.
You can let us know if you want to do this in Spark.
Yeah, I mean, the MLflow part is going to be interesting. So you can talk about some parts of that, and then also the MLflow integration is going to be good. Let me see if I can rally up the people. All right, guys, we're starting in about a minute or so if you can come in. All ready? I'm going to start. Okay, we're back, right? Yeah. Okay. Hello. Do you guys mind taking your seat?
Test.
Hello. Do you mind taking your seats, please? We're going to start. We're getting started. Do you mind taking your seats, please? Thank you. Okay, well, second talk today is from Matej Zaharia. The man hardly needs any introduction. He's the original creator of Apache Spark and also the co-founder and chief technology officer at Databricks, and he's also the person who's behind MLflow. So he's going to give us an idea of what MLflow is about, joined by Clemens, who's our director of product marketing, and then we're going to have a demo about some of the features in 1.0 from Richard Zhang. So without any further ado, please give a warm welcome to Matej Zaharia.
Okay. All right, thanks a lot. Can you hear me? Sounds okay. Okay, great. So yeah, so I'm going to talk a little bit about what's new in the latest release of MLflow, the 1.0 release. And for those not familiar with it, we launched MLflow as an open source project just about a year ago, so last June at the Spark AI Summit. So it's been 1 year of getting feedback and so on before we could have a stable 1.0 release. And then I'll also be joined by Clemens Maywold, who joined us very recently from Google. So Clemens was the first product manager on TensorFlow and also the lead product management for the TFX internal machine learning platform there. So we're really excited to have him here, and he's working on machine learning in general at Databricks, but also he's personally acting as the PM on MLflow. And we'll also have Richard Zhang, who is an engineer that's been working on a bunch of the new features in the release that we want to demo. So the plan is I'm just going to have a little bit of an intro of what's happening in the project. Then Clemens will give both an overview of MLflow for people not as familiar with it and a little bit on what's new and what's coming next. And then Richard will give a demo of some of the new UI features that we've been building especially for visualization. So just to start with, so basically the background for MLflow is that we saw people are often building a new kind of software platform for machine learning powered products. So like Flock is a great example of that, but it's also happening in many other organizations of all sizes. So people realize that when you have a machine learning application, you need to keep it fed with data, you need to monitor it, you need to exchange things like models and data sets and featureization steps and so on across different teams, and it really helps to design a platform to manage the machine learning lifecycle. So that's kind of the motivation. So to give a little bit of background on what goes in there, so machine learning by definition is programs that generalize from data, so you need to put in data, and then if your thing works, you have to keep feeding it new data and updating it in the future. So the raw data and the extract, transform, and load ETL are important components of machine learning. Then you've got maybe some featureization steps, and definitely some training steps to train a model. And then you also have to actually do inference, score data or serve the model in real time. We just heard about ONNX Runtime as a way of doing that. And then also monitor how that's doing, get alerts, debug when things are going wrong. And all this stuff feeds back into earlier stages. So if you notice there's some bug or some poor behavior, maybe you have to change the way you're transforming the data. Maybe something changed in one of your data sources. Maybe you have to actually explore new training algorithms and new features and so on. So you've got this life cycle that sort of, is pretty complex, and you have to be able to easily feed back information. And then the other thing that makes it complicated is that there are a lot of different frameworks to do machine learning. So normally in software, like if I'm building, say, a web application, okay, there are lots of different web frameworks I could use. There are lots of different databases I could use, but I'll just pick one of each and I'll stick to it. And that's all the software I have to learn. But in machine learning, you want to get the best possible model. So over time, it's really great if you can actually experiment with the latest and greatest algorithms to come out, and the latest and greatest featureization steps or ETL libraries, and also just all the data sources in your organization. So most ML platforms and applications we see have to combine a wide range of these frameworks. They don't just say, okay, our company standardized on just one, machine learning library. So you have, your platform has to support that as well, has to support this portability. And then there are other challenges across these, so like tuning your application, deploying code from all these frameworks in a consistent way, managing models, collaborating, and so on, that just affect, it could affect many types of applications, but they also affect machine learning. And so as a result of this, people are starting to develop these very specific infrastructure components for machine learning that, that make this easier. So our goal in MLflow is we saw this pattern of people designing machine learning platforms at a lot of companies, both the large kind of tech giants, but even enterprise companies we talk with that have a much smaller data science or ML department. And we saw there's no open source ML lifecycle platform, so we decided to start MLflow as an open source project in this space, and in particular the main kind of design goal we had is because people are using this wide range of infrastructure and processes to make it very easy to plug in different products and different libraries and so on through APIs. So MLflow is really designed in an API-first manner where we don't think about, okay, here are the 5 machine learning libraries we'll support, or here are the 2 deployment modes, but rather we make it easy to plug in whichever one you have. And this is why, for example, we were really excited to see the team here contribute the ONNX model format, and it just kind of fit in and it works with all the other features of MLflow. Okay. So as I said, the project started about a year ago. So one thing we've been excited by is, when we started, we didn't know whether there would be interest in this kind of ML platform, and especially in building kind of on an open source one and a set of APIs. But we've been really excited with the growth of the community. So we counted like over 100 different contributors to the project from at least 40 different companies, when we can tell what company they're from. Microsoft is one, obviously, but there are others as well. And the project also gets around 600,000 monthly downloads on the Python package index. Now that's, it could be lots of automated scripts and stuff like that, but it's actually relatively high for a data or ML project. So just in comparison, for Apache Spark, which was started in a university, it's a bit different, but it took about 3 years to get to this many contributors, and now it's got about twice as many downloads per month on PyPy. So we're really excited with the growth, and we hope that people are successful building on it. And we also, we're also working as the community grows to make it easier to contribute, to have things like a really good process for submitting new features and so on. Yeah.
Do you have any information about the, besides the downloads, whether how many people are deploying it, using it?
Right. That is a good question. Yeah. So we didn't put any kind of tracking, in the project, because we thought that would be weird if, like, the open source project you deployed is tracking usage. But we did do some surveys, and we also have on the Databricks cloud, we know, customers using it and like active users and so on. So we do have, pretty large fraction of our sort of larger accounts are using MLflow in some way, and we're getting very regular feedback from those cloud users. And we ran an open source survey as well, where we got, I forget exactly how many, but I think like 100 to 150 companies, distinct companies, people who replied. Yeah, so it's hard to track, to track this exact thing, because we didn't want to put some tracking software in this thing that says it's alive and it's calling home and stuff. Yeah.
That's what I was gonna say.
Yeah. In the cloud setting, it's easy. And in the cloud setting, we also, we talk to them. We're like, why did you stop using it? Did we do something wrong? Or someone's on vacation, So that's what you can do there. Yeah. But obviously, we want to continue getting feedback. So yeah, we've been excited with this, and we want to, that part of the goal of having, 1.0 was also API stability. So both the users, but also people integrating with it can do some work now and have it continue working for like many years in the future. So we don't change stuff underneath them. So that's why we're doing that. some users and contributors, these are actually ones who spoke about this at our past meetups and also at the Spark AI Summit. So you can actually find most of the talks online. I think all the Spark AI Summit talks you can find online. So these are like, some of the ones up there that wanted to have their logo and stuff listed as part of that. And then the other thing that's happened as a result of this that we're excited about is just what MLflow can integrate with. So as I said, with machine learning, you really want the ability to support many libraries, many data sources, maybe many deployment backends and so on. And one of the reasons we made this open source is because we felt like no company can build something very comprehensive on its own. So like we'd rather have a community effort to make all these things work together. So when we started the project, this is kind of what we supported, one programming language, a few ML libraries, and a few deployment systems. And now, all these things have grown. So we got our API contributed from the community, from our studio, Java API we built at Databricks. We got lots of ML libraries with plugins, and also like, most major cloud storage backends, ONNX and other deployment backends as well. So we're excited to see this list going. Actually, these are just the things in the main MLflow repo, but there are also external things like Selden Core model serving that support MLflow. And then the final thing I wanted to mention is just what does the 1.0 release mean? So first of all, it means API and like data format and data model stability for the original components we put in, which hopefully makes it easier to build apps or your own internal platform on it. And it also can mean time to start adding some new features and components beyond what we put in. So with MLflow, our focus is not so much like we don't want to replace, training libraries or even serving systems or whatever, but we do think there are kind of spanning components like this data, data governance type thing, monitoring, model registry that, that can span the whole life cycle. So that's what we're looking at. So to talk about that stuff, I'd like to invite Clemens, who will go into detail on that.
Thanks, Matej.
Okay, thanks.
All right, my name is Clemens. I'm the product manager for MLflow. And just to give me an idea of the audience, how many of you have used MLflow beyond like just running tutorials or like looking at the docs? Just to show of hands. Okay, that's great. Because I'm going to adjust how deep I go into just the general topic of what is MLflow and what are the components. So first, I'm actually going to go through the main components as they exist today that are part of 1.0, explain what each one of those actually do. And then I'm going to go through some of the new things that we introduced with 1.0, and then I'm going to talk through the roadmap. So first and foremost, the most commonly used component of MLflow is actually the tracking component. So that really allows you to track experiments and runs and keep track of all of the work that you do such that you can go back and compare different runs. And also it helps you actually make it more producible for you. So that's the most common one, and I'm going to go into more detail on actually what that means and what we're tracking. The second one is called ML projects, which is a format that packages up your machine learning code such that it's easily reproducible. I'll also show you what that means, but it basically captures all of the environment and the dependencies such that you can say, I want to rerun this exact same code, and you can depend on getting the exact same result. And then last but not least is a model format, and basically an on-disk format and a convention that allows you to package up models that come from many different machine learning frameworks and store them and deploy them in a common way. And there's an interesting story, and like the pro topic today is actually how the different ML frameworks and MLflow model formats and ONNX actually interplay with each other. So first on MLflow tracking. So you can call the tracking APIs in many different ways. As Matej just mentioned, they're available in 3 different languages. You have Python, Java, and R. And you can call them from notebooks. So that includes all of the notebooks that you may run on your laptop. You can also call them from the Databricks hosted notebooks. From local apps, you can really just like run like a Python script on your laptop and call the tracking APIs from there. And of course, also from cloud jobs. If you automate your workloads, you can also call into the tracking server. Once it's in the tracking server, that server is basically the backend for our front end. So you can see you can actually we have a nice web app that allows you to search all of these runs and actually find the best ones and sort by different metrics. But there's also an API so that you can access this tracking server such that you can actually build your own applications on top of MLflow. And as we've seen also at Microsoft, there's a lot of companies and platforms that have started building on top of MLflow and using the tracking server for their own purposes. So what is being tracked? Parameters are just key value pairs that are being tracked. Then metrics, I'll show you what that means. That's the most meaningful thing really for machine learning workloads where you track metrics over time. Artifacts. Artifacts can be arbitrary files, blobs really. Machine learning models are a special kind of artifacts that have their own API. And then also additional metadata in terms of where did the source code come from that you ran? What was the Git hash so that you can reproduce it? If you run it on Databricks, we actually give you the exact revision of that notebook that produced that run so that you can go back and look at the code that produced that run. Projects, as mentioned, are both a convention and a format really that packages up your code such that you can more easily reproduce it. And it's really a snapshot of your code, the configuration of your code, and in this case, that really means your environment. So I'll show on the next slide what is part of an ML project. And data, it doesn't really package up your data. You can store your data alongside your ML project, but often you would just basically store the metadata and the pointer to what data you used so that you can more easily reproduce it. And then once you define an MLflow project, you can run it locally. You can just say MLflow run and point to that project. Or we also have a functionality that we call remote execution, where you can say, take this project and submit it to, let's say, a Databricks cluster and execute it remotely. And I'll also talk about later, the community is adding support so you can execute these projects on a Kubernetes cluster, if you want. So this is an example of what an MLflow project looks like. And as mentioned, it's really definition by convention. So this is a directory. It has a file called ML project. And in that file, you see the configuration of that project is, or the environment is specified as a conda environment. So it says in conda.yaml, you'll find the dependencies. And then you define entry points. And those are really the entry points that you would execute when you call that project. And in this case, it's really just running a Python command. You say Python main.py, and it takes 2 parameters, and those parameters are also logged with the run. So once you've defined an ML project, and as you can see, it also contains the code. So, sorry, was there a question? Or, okay. Once you've defined that project, and often it's like in a Git repo, you can say MLflow run and just point to that directory. And MLflow will know that it's an ML project because of that file. It will find the entry point and run that code for you. And of course, you can also call that from the MLflow Python API in this case. MLflow models is really the core component for those who train machine learning models and actually want to log them and then use them in inference and deployment. So you can log models the same way you can call any other tracking API from all of the different sources. And the MLflow model format is really a package of the different serialization formats that the machine learning frameworks provide. In each MLflow model, you can store different flavors of a model, and I'll show you why that is very meaningful, to have multiple flavors for the exact same model. And then once you've defined, or once you've logged a MLflow model, we provide APIs and utilities to deploy these models in all of the common ways that you have encountered. One of the most common ones is package it up as a Docker container and provide a REST API. The Python icon means pyfunc, which means that the model is basically exposed as a Python function. You can call it anywhere where you can call a Python function. A very common way of deploying these models is for batch deployment. So there's an easy way of taking an MLflow model and deploying it as a Spark UDF to score a batch job. And of course, you can also easily package it up and push it to inference services such as Azure ML or AWS SageMaker. And the key here is that no matter where a model came from what machine learning framework you used, all of this deployment works consistently across all of these frameworks. Again, this is what it looks like, and here you can see the convention. So a model is written to a directory with an ML model file. And in this case, it's a TensorFlow model. And you can see we stored 2 different flavors. The first one is the TensorFlow flavor, which is the standard serialization format of a TensorFlow model, which is called the saved model, which is just a proto file. And then the second one is the Python function flavor. That really just means that you can load this model and just call it like a Python function. I think I have this highlighted. Yes. So if you're familiar with TensorFlow serving, you would basically just use the TensorFlow flavor and pull the saved model and use that for inference. And you can also just use it in any tool that can call Python code. So these are the 3 components as they exist today and as they exist in 1.0.
Question.
Yep.
When you deploy to Spark, then you go to the Python wrappers. Does it do it more natively depending on the model?
So I think for all of the common model formats, it's using the PyFunc. I think for MLlib, that's probably different. Matej, is that true? Yeah. Because MLlib is like Spark native, but for all of the other frameworks, it calls into Python. So that's what exists today, and that's the common components that you're familiar with. And now I'm just going to talk through some of the things that we released new with 1.0. And if you're following the GitHub project, as you can see, 1.0 was released. This just says the relative day, which was 2 days ago, I think 1.5 weeks ago or 2 weeks ago. So there's a lot of things that are new in 1.0, and I encourage you to go to the GitHub repo and read the release notes. It's a pretty long doc, but I'm actually just going to walk through some of the key components, and then we're actually going to demo to you a few things that are new in our front end. The first and most noticeable feature is probably support for logging metrics with a user-defined step. And I'm just going to walk you through what that means. In many cases, people log a single metric at the end of the training run. Right? So you train a model, and at the end, you know this is my loss, this is my accuracy, and so on. And it's a single value of a single metric that you log once when you're done. And we show that in a table, and the visualization of that is very uninspired because you just show a block that says this, I don't know what we're showing here, dr squared value, right? But often you don't want to just log one value of that metric at the end of the run. You actually want to log the metric as you train and as the metric develops over time, especially in all of the stochastic training algorithms that we use these days. You train in mini batches, and often these metrics, you get as streaming metrics calculated for each mini batch. So what you actually want to log is accuracy per mini batch, or loss per mini batch. In many cases, or until 1.0 actually, in MLflow, the way that it was visualized was in the order that these values arrived to the tracking server. So here you can see 3 values for a metric, and you can actually see, you cannot see it on the horizontal axis, but really the x value for this is 1, because it was the first metric that was logged, or 1, and then 2, and then 3. And that's usually not the most meaningful information that you want, because if you're familiar with training frameworks like TensorFlow or PyTorch, you actually want to visualize metrics over the global step, right? Which is the mini batch size times the number of steps that you've taken, or the epoch of your data, like you train over 5 epochs and you actually want to show the number of the epoch. So in 1.0, we added the ability in the log metric API to define a step. And that's really the most flexible way that we can provide this, right? Because now you can log this metric for this step. And if you have multiple metrics for the same step, you can do that as well. And it actually allows you to specify for which step value this metric is. And if you have multiple processes that log metrics in different orders, it doesn't matter because you actually specify the horizontal axis. I'm not going to talk you through this screen cap because Richard is actually going to give you a much, much better demo of this feature once I'm done talking. The next feature I wanted to highlight is improved search. So we've seen a lot of our customers and users very intensively use MLflow. In many cases, they use it for hyperparameter tuning. So they run programs that actually generate hundreds or thousands or tens of thousands of runs. So searching becomes very meaningful, right? Or you have a big team of 10 people that all log to the same server. So discoverability of all of these runs is really important. So the search API now supports a nice and simplified version of basically a SQL where clause, where you can specify for the different parameters and the different metrics, search strings, and you can like chain them together with expressions. And then here you can see how that looks in Python code. So you can really just use the MLflow client and search for the runs that, in this case, have a model parameter that's logistic regression, and the metrics error value smaller than 0.05. And of course, you can use the same search queries also in our web UI, where you can filter down all of the runs that you have. Because really, in some cases, you end up with thousands of things. Matej pointed this out earlier. One of the goals that we have and like one of the motivations behind MLflow is really to provide a standard and to have it really used widely. And what it means is we really need the community to contribute and add support for more and more storage backends and model formats and so on. So here you can see all of the storage backends that were already supported. We already had support for S3, Blobstore, and so on. And HDFS was added in 1.0 because it's a very commonly requested feature, and also a lot of our customers were using that on-prem. The ONNX model flavor is something that was contributed, and we're very happy with this to actually have ONNX support in MLflow. And this is now the expert topic, because ONNX really, if you think of it, is not really on the same level as all of these machine learning frameworks, right? You just saw the slide where there's so many different machine learning frameworks, and ONNX is really a format that you can convert all of these models to, so that you can deploy it in the same way, right? So now, for those of you who can follow, ONNX is a serialization format and a runtime that you can convert all of these ML frameworks to, and MLflow models is a serialization format that can store different flavors of machine learning models and provide common ways of deploying them. But of course, those two are not the same. So you can train a PyTorch model, convert it to ONNX, and save it as an ONNX model in MLflow, right? That's a perfectly valid use case. Or you can train a PyTorch model and just save it as an MLflow model. So that distinction is actually important. And that's why you've also seen here ONNX is part of this list, because in MLflow it's a model flavor. But really, ONNX supports storing TensorFlow models and PyTorch models and many other formats in that format, if that makes sense. And last but not least, I think a very commonly requested feature. We already built Docker containers to deploy MLflow models on cloud services, but a lot of our customers just really want the Docker container so that they can go run it on the Kubernetes cluster. So we added this command that easily lets you build a Docker container from an MLflow model. And again, it doesn't matter where that MLflow model came from, whatever machine learning framework you used, this command is the same. And then you can just Docker run that container and perform inference with it.
Can you run the tracking server in a Docker container?
Can you run the tracking server in a Docker container? I believe so, yeah?
We don't provide one.
Yeah. We don't build the container for you, but you could build it yourself. All right, so these were just some of the features that we shipped with 1.0. And now let me just quickly talk about some of the things that you can expect in the future. So we actually did this survey a while ago where we got feedback from the community. And as you can see, the #1 requested feature was model registry. And this is basically priority weighted ordering of these options. A telemetry component refers to actually monitoring the performance of a model when it's deployed. Multi-step workflows was commonly requested. Built-in hyperparameter search, and manageability and scalability. So on hyperparameter search, actually, we're going to show a visualization for this. There's a lot of different tools out there that people use, but we really want to enable logging all of these different studies and trials and visualizing the result of them really well. And model registry is actually the main component that we're working on right now.
Sorry, one question.
Yep.
The list, right? It seems that a few of these things are overlapping with some of the strength of, say, Kubeflow.
Yep.
How are we playing nice or not playing nice with another open source community that neighboring Java?
That's a great question, because also coincidentally, I co-founded the Kubeflow effort.
I figured.
It's actually very different. So Kubeflow, there's two different ways to, or like two different things to refer to, right? Like one is Kubeflow as the GitHub org and the community where a lot of projects are contributed to, like Catip, right? And then there's Kubeflow Pipelines, which is a project that the Cloud AI team runs, right? So Kubeflow in general as a framework to help you allow to run things more easily on Kubernetes are completely complementary with MLflow, right? So there's no reason why the community shouldn't get behind like building a nice deployment of MLflow on Kubeflow, which really means like building a nice deployment on Kubernetes, right? So I think that would be great. I don't think, at least last time I checked, that the Kubeflow project actually had a good tracking solution. So in that case, it's even more complementary.
But my understanding is that we are starting very complementary.
Mm-hmm.
They're creeping this way, and MLflow is creeping that way.
Yeah.
So that is either a collision course or a good way of
Yeah.
playing nice with each other.
I think it's. I think both communities are like pretty open and pretty friendly and have meetups. So I don't see a collision course right now, but we can like talk about that later. There's especially both have companies behind them, right? And then like there's managed offerings, and I think it gets complicated there. Yep. And actually, like we are working with the community on Kubernetes support, right? Because that's very common. So on model registry, that's the main priority that we're working on right now. Because as you've seen, a lot of our customers now have easy ways to train models, to track those models, to log those models, and to deploy them. But many of them end up with hundreds or thousands of models. And the deployment lifecycle of a model is actually pretty hard. In many cases, our customers want to integrate those with CI/CD systems, want to build in model validation, and so on. So the model registry will really allow you to have a version-controlled registry of your models. So in many cases, you don't have one model and then you move on. You have many, many different versions of models and keep updating them. As mentioned, the deployment process of a model is often a multi-stage process. That's a life cycle. You need to stage it, you need to run experiments, you need to deploy it, maybe roll it back if you have a production issue. And then also monitor these models in production and allow our customers to easily pull back some of these metrics to MLflow. So that's something that we're actively working on right now, and that's on our roadmap for the next couple of quarters. Another interesting project that we're working on is auto-logging from common frameworks. As you know, right now, you can call the MLflow APIs from many different places in many different languages. For the most common machine learning frameworks, we can already guess what you want to log, right? If you define your TensorFlow graph and you have eval metrics in that graph, you probably want to log those eval metrics. So we can actually make some assumptions and introspect your code to automatically log some of these metrics to MLflow to make adoption of the product much, much easier. And we're actually starting with TensorFlow in that regard. The next one is a parallel coordinates plot that's really useful if you do hyperparameter tuning, and we're going to demo that in a minute. And I just mentioned one of the contributions that we're working on right now is being able to remotely execute projects on a Kubernetes pod. So I mentioned earlier, when you defined an MLflow project, you can either run it locally or you can execute it remotely. And the Kubernetes will be one of the targets where you can run that code. And then last but not least, Databricks has another very successful open source project called Delta Lake. You can check it out at delta.io. And one of the very interesting features of this is it provides you a feature called time travel, because it actually keeps a write-ahead log and allows you to look at your data at a specific point in time. And if you think about this, often when you train your machine learning model, you actually want to know what your data looked like maybe a week later if you want to reproduce the same model. And if your data has changed in the meantime, it's very hard to reproduce the exact same way that the data looked like. And if you have a large amount of data, it's not really feasible to make copies every time you train a model. So if we integrate MLflow with Delta Lake, there's a very obvious and very useful data versioning story where you can say, this model was trained on this data on this timestamp. And we can actually go back and tell you exactly what the data looked like at that point in time. So there's a lot of really good features bringing those two together.
The way it's currently done or planned to be done, is it general in the sense of, the way I'm asking it is, there's a bunch of other things that maintain versioning, right? Either the Git LFT or the databases can maintain versioning well, and a bunch of other objects that know how to do versioning. File systems that are good at versioning. Is it sort of, so the tying in is particular to Delta Lake that was being built, or you have a generic versioning layer that we can implement differently?
Yeah, so I think the design principles that we try to follow is always API first, and basically design it in a way that you can plug in different backends. And we basically provide reference implementations or the solutions that our users are asking for, and then you can extend that. So my expectation is, this hasn't been designed. We have customers already using them together. You can already do this if you code it yourself, right? You can log as a parameter the exact timestamp and all of the metadata you need, such that you can then go back and pull the exact same data. But my expectation is that the APIs are going to be general enough that you can use it with Delta as an implementation, or that you can extend it in and write a different plugin, basically, similar to the other components.
When you get to do it, if you do it, all the development openly, I think we would love to collaborate on this and a second reference implementation for any versioning system that we let's say, make sure that for the get-go the APIs are there. This is super important.
Sounds great. Yeah, we should follow up on this. All right, and this was the last named one, and of course, as you can imagine, there's much more coming, both from the team that's working on MLflow directly and also from the community, because we get contributions all the time. And with this, we're just going to jump into a real quick demo to look at some of the new UI features that we have coming up. This. All right. Oh.
Hi, I'm Richard Zhang, and I started working on the Databricks notebook and workspace product from 2017. And recently, I've collaborated with the MLflow team to work on some of the nice visualization features to make MLflow easy to use. So just to show you a pre 1.0 version of MLflow, so you can go to the run page and click a metric. You will see the history of the metric, and you can sometimes see a trend, but it's not very amazing and not very interactive. And in MLflow 1.0, we add a lot of features for you to visualize your metric history and do comparison between runs. For example, this is 1.0 version, and if you drill into any metric, and you'll see you have a lot of controls that you can tweak around. You can see, we can toggle points and line smoothness. And also, you can compare multiple metrics trends. And also show the wall time. And as Clement showed that we now support a step when you log metric. So when you log the step, you'll see a different plot based on your step. And also, when you compare multiple runs, you'll see multiple runs, multiple metrics from same metric, metric 0 from multiple runs showing in the plot. And you can bring in more. And you can toggle the y-axis log scale. And another nice feature of that is that, for example, you're exploring your metrics, and you do want it to share with your friends that this URL. So it will be a reproducible, those metrics will show, and they are memorized in the URL. So that's immediately available in MLflow 1.0. So go ahead and try it. And also, there's a work in progress. Some of you might have already seen this parallel coordinates plot that I'm working on. It's like a work in progress. But before I demo that, I'd like to switch to my deb branch. It's literally a deb branch, so if you see a flash of error, it's completely normal. Okay. Oh, this is a... So I'll start at start MLflow server at a directory that I have some of the pre-existing runs to show the parallel coordinates plot. Okay, so say I have an experiment that I have some nested runs, and I wanted to do hyperparameter tuning. I wanted to select all the runs and do a compare on all those runs. And you'll see here, this is a work in progress parallel coordinates plot that you have all the parameters pre-selected, and you can select multiple metrics. And we have a scale for the metrics on the right-hand side, and then say I want to select training time and loss, test error, and you'll see if I drag and drop those ones, that the scale will change. Say now I wanted to focus on the loss, and I want to minimize the loss, right? So I can select a range that is on the lowest part of the loss and see if I can see some trends. And I noticed that the learning rate, if I have lower learning rate and maybe have a larger batch size, it looks like it produces better, less loss, right? And to verify that, I can select a range on the low learning rate and then higher batch size. And I can confirm that those parallel coordinates plot on the loss part, those runs generates less loss. And the advantage of parallel coordinate plot is that it gives you a holistic view of different dimensions. We have the scatter plot, and you can select multiple. You can select different metrics on the x-axis and the y-axis, but it's just two-dimensional. Parallel coordinates plot really give you the ability to have a holistic view of how your parameter works and how to generate the desired metric output. That's it. Thank you so much.
We'll take some questions for Clemens, Richard, and Mateo. Do you guys mind coming over here so we can have the audience? And also, if you have any questions for Subru and Avrilia, they'll be here as well. Anybody? All right.
Yeah. So do we have any plans to support the distributed TensorFlow training or PyTorch training by using MLflow?
Yeah, I can take that. MLflow is orthogonal to the training framework, and whether it's single node or distributed, right? So you can, no matter how you train your machine learning model, if you call the MLflow lock APIs, it will log to the tracking server. If you want to log from worker nodes, so if you, let's say, distribute TensorFlow, you have a parameter server and multiple workers. If you want to log from each worker, you can do that, right? But often you would actually want to log from the parameter server because that consolidates all of the updates to your parameters. But how you distribute your training or how you log to MLflow is actually an orthogonal question.
So actually my question is, So I see the slides is coming is to deploy the MLflow run project to Kubernetes.
Yep.
So I mean, for that part, is there any plan to support the distributed training?
Right. So in that part, so if your deployment code, so let's say you use the I think in Kubeflow there's a custom CRD for TensorFlow training, I think. If that job deploys a distributed TensorFlow model on Kubernetes, then that's the code you wrote to distribute it, right? Like MLflow wouldn't add any additional code to that, right?
Yeah.
Any other question?
So my question is, how would the MLflow overlap with TensorBoard in terms of like tracking?
Integration with TensorBoard.
Yeah. Do you want to?
Yeah, I can talk about that. So yeah, I think, yeah, we want to make it easy to use TensorBoard together with this. One of the things you can do now is save your TensorBoard event files as an artifact and then have them, have access to them later. And actually, we'd like to build integration in the UI as well, where you can select a bunch of runs and then launch a TensorBoard that compares with them. In MLflow, we focused especially on kind of the end metrics about like how a application did at the end. So it's less focused on letting you debug in the middle of a run, but it's more focused on like after you did, 100 different runs, how do you find a good one? So that's kind of what we optimized our UI for, but we want to make it easy to use both. Yeah.
So any thoughts on putting MLflow in the Apache Foundation or any other sort of general
and some kind of, we're looking at these kind of things longer term. Like right now, it's still early on, and we want to just move quickly, but definitely long term, we want kind of a stable place for it. Yeah. And we're also looking at, like, in general, scaling up the development process, like making it easy to propose something, to have a way to sort of review, like, what's in scope, what's not, agree on stability, that kind of stuff. Yeah.
Two questions, if you please. So first one is distribution, extensibility of MLflow. What is the architectural solution for that? For example, if our company wants to have some new flavors of models to get added or deployment targets and actually don't want to share it with general public contributing back to MLflow, how easy is it? Is it pluggable approach or something like that? That's the first question. And the second one, really small. You've been showing a very nice slide about what's on the roadmap. So is there any timeline to this roadmap already attached? When should we expect new versions?
Yeah, sure. So yeah, I can start with the first one. So for extensibility, we did try to set it up so you can have your own extensions inside your company that, you don't need to get anyone to commit anything to the open source project, because it would be really bad if everyone had to block on this one, repo to get this stuff in there. And the way that's done is a lot of what you can do is in terms of like just general kind of key value pairs or general data formats like files. So for example, for the flavors, it's a YAML file, and you can add however many flavors you want in a model, and downstream tools will just ignore a flavor they don't understand. But if your deployment framework in your company understands it, it can use it. So anyone can come up with their own flavor and do something there. And if you want it to be kind of, you want it to be public and have a public, implementation for everyone, you can do that too. For another example is these tracking servers. So actually on Databricks, we have our own, tracking server that's integrated into like the Databricks, SaaS product. And Azure ML also has an existing tracking service that they want to plug in. And so do other companies. So actually, that is something you can plug in through a Python module, and anyone can write a tracking server plugin and put it in there, and the user code doesn't have to change. Another like final example is through tags. So on these runs you can put in any key value pairs you want as tags. And so people are adding custom things for their environment. For example, you know, in Databricks, we made it so if you're running in a Databricks notebook, we remember the notebook ID, and we even take a snapshot of it and like show it to you later. So that's done as a tag. So you know, any client can, you know, can add their own tags. So that's the way we're approaching this. Hopefully it works for people, you know, as long as you've got this data model.
But Matej, we also had the extension for people who can actually use the plugin architecture to have their own artifact storage, right?
Yeah, also, yeah, plugging in an artifact store is another one. So yeah, there are some things yet that aren't as pluggable. For example, I'd love to have UI plugins. We don't have that yet, but I think it would be nice if someone, you know, has a good idea on how to do it. That would be great. But that's kind of what we're hoping for. And for roadmap.
Yeah. Yeah, so on the roadmap question, let me go through some, like actually the different items. And it's hard to put like general dates on those because they actually depend on different parties sometimes. Some of them are contributions, right? So let me just pick a few examples. The parallel coordinates plot that I mentioned, like you've just seen a demo, that's going to be available when? Like pretty, like
start reviewing it tomorrow.
Not to put you on the spot, but pretty soon.
Next meetup.
Right, next week. Now you have a deadline.
Right now, it literally only exists in my dev environment.
Okay, okay.
It won't be available this spring.
Yeah, I guess on the GitHub.
Yeah. So in like on the order of a couple of weeks. So that's pretty soon. The Kubernetes example that I mentioned for remotely executing, that's a contribution. So really working with the community on this, and like as fast as the community can go, as fast we can review this. So there it's harder to put a hard date on this. On model registry, that's going to be a very like long-running project because, as you can imagine, there's different stages at which we can deploy a model registry. The fully blown, like full lifecycle management solution will probably take longer. We do expect to have an MVP for this in the next quarter, where the most common use cases of actually having a version-controlled model registry will become available in the next couple of months. That's just some examples, but as you can see.
Okay, we got a question over here.
How will this be integrated into like Azure pipelines? Is there going to be some integrated MLflow server, or is there an MLflow server as a service in Azure, or is this something we run on a separate VM and then just do regular command line commands? So
Azure actually hosts MLflow, and also Azure ML started using the MLflow APIs for tracking. So you can use the exact same APIs to track on Azure ML. So I guess the answer is you can use their hosted version of MLflow, or you can also run your own MLflow like server in your own VM, right? Like that's really up to you. Okay, but so Microsoft, I think we announced this at the last Spark AI Summit, really got behind MLflow, and they're starting to use both the server components and also standardizing on the APIs.
If you send me some mail, I'll show you the link to the presentation from Spark Summit that shows integration with ML Azure. Any other questions?
So one of the things you were very briefly mentioning was the auto tracking, and the way you hinted it seemed like we can go into various specific frameworks, and within that framework we can figure out what we need to do. The thing that Subru was showing in the demo is our take on the problem, which is a bit different, is we do sort of static analysis of Python. We have a database of you know, the things we understand and care about that you can extend on your own and go there. Thoughts on that?
Yeah. So this is, as you mentioned, like static analysis and like almost like code generation or like code injection, right? I think there's different, like we're working through different design approaches. Some of them involve, so you can imagine, let's actually pick TensorFlow as an example because it's easy, and because there's also what is called TensorBoard X, which is used with PyTorch, right? So the way that TensorBoard works is TensorFlow writes out files, like event files on disk, and then TensorBoard reads those files. So you could imagine, with the knowledge of where those files are written, we can just take those files and lock those symmetrics into the MLflow tracking server. That's one option. Another option is like monkey patching the APIs in all of the different frameworks, that at the place where metrics are being computed and generated, we actually inject code that logs it to the MLflow tracking server. So we're working through different options in this. From a product and from an experience perspective, the goal is really to create the least amount of work for our users. While at the same time it needs to be extensible, right? Like sometimes you can do magic of saying, oh, we can automatically track everything that we think you may want to track, but you should still be able to like track more, right? And have an escape hatch. Yeah.
Subru, you had something? Any other questions? Going once, twice. All right, give a big hand to our speakers today. Subru, Avrilia, Clemens, Matej, and Richard. And I really want to thank Carlos and Subru and Avrilia and Microsoft for really hosting us. And I hope you guys have a good evening and safe driving. Hope to see you back again in San Francisco. We have tried to do this back and forth, so hopefully we'll see you again. Thanks a lot for coming. Cheers.